In this presentation, we'll discuss the filter amplifier and Precision Filter's distributed gain topology. Using distributed gain can be very effective against large out-of-band signals and can be applied to greatly improve the overall signal-to-noise of the in-band signal of interest. And by adding the programmable amplifier, we'll be able to gain up the signal of interest and use the filter to eliminate signals that are outband that we don't want to measure. Precision Filters always distributes our amplifiers in a what we call distributed gain topology, where we apportion some of the gain before the filter as pre-filter gain and some of the gain after the filter as post-filter gain. This allows us to set the pre-filter gain so that we do not overload or overrange on the signal plus outband energy at the input to the filter. We use the filter to eliminate that outband energy and then gain the in-band signal up the rest of the way to achieve our desired volts per measurement unit at the output. We always include in our instruments an overload detector at the input of the programmable filter, because an overload condition that occurs anywhere within an amplifier will really destroy your data. You'll have signal creation, nonlinearity, and you can have DC shifts in the data when the signal overloads in the filter. The filter will mask an overload condition at its input. The output of the filter may look like a perfectly reasonable signal, but the input could be overloaded, and if you don't have an overload detector built in the amplifier, you would never know. So we always include a pre-filter overload detector with our instruments. As an illustration of signal clipping and what can occur, we'll just take a simple quarter strain gauge bridge where we desire to measure a full scale of 2000 microstrain, and we calculate that with a gauge factor of 2 in a quarter bridge configuration and 10 volts of excitation, that we require a channel gain of 2000 to give us 10 volts full scale out for 2000 microstrain. Now, in a normal situation where we don't have any noise coupling into our circuit, we'll have sinusoidal strain measurement, and we'll get a nice clean signal out. But now if we subject the input wiring and sensor to noise, the noise riding on the signal, first of all, in the time domain, we can't even see our signal or really make it out. But we also notice that in our amplifier, which has plus or minus 10 volts of signal swing maximum, that there's portions of this green signal trace that are exceeding the maximum signal swing of the amplifier. When that happens, we call that clipping. And when clipping happens, we have what I described in the previous slide, nonlinearity. In the amplifier, we can have signal creation due to this nonlinearity and DC level shift due to the clipping. So we do not want to have clipping. Clipping invalidates our data. So one thing we can do to avoid the clipping is to cut back on our gain. And in this example, we cut the gain back to a factor of 200, and now the signal plus noise does not hit the maximum signal swing or those red horizontal lines in the amplifier. We're good. We don't have clipping now. But the problem with this is that we had to leave 20 dB additional headroom in our amplifier and our downstream A to D to prevent the clipping. So our signal to noise ratio, because of having to leave this headroom, is not going to be optimal. So if we add a low-pass filter and a post-filter gain stage to our topology, or the precision distributed amplifier topology that we talked about, we can handle this outband noise. What we do is we set the pre-filter amplifier to a gain of 200. We filter out the outband noise that we do not want to measure, and then we gain up the signal the rest of the way with a post-filter gain of 10, so that we achieve an overall gain of 2000, and we see a nice clean signal on the output that's gained up as we desire. So this illustrates the importance of the distributed gain topology and how you can deal with a situation where you have outband noise that's larger than the signal you're trying to measure. This can often happen in underdamped transducers such as accelerometers that have very high Qs. You're measuring shock with a sensor, and it's easy for that shock impulse to excite that outband energy and create signals at the output of the sensor that are larger than the in-band signal you're trying to measure. Important to have a filter with distributed gain to combat that. So to summarize, to protect against outband signals that are larger than in-band signals, you must have the gain separated into pre-filter gain and post-filter gain around the filter. We'll set the pre-filter gain so as not to clip on the outband energy plus in-band energy. We'll filter out that outband energy with the low-pass filter and gain up the rest of the way with the post gain so that we reach our required full-scale output, signal output.